Hello everyone, my name is Wenqi Cai. I'm a master's student in Estimation, Modeling and Analysis group in King Abdullah University of Science and Technology. Today, I would like to share my work, an extreme seeking control-based approach for solving the alignment problem of mobile optical communication system. First, I will give a brief introduction about the optical wireless communication system, the OWC system, and then talk about the motivations and objectives of this work. Next, I will introduce the experimental setup and followed by the main part of this work, the proposed two-step control strategy, which consists of coarse alignment and fine alignment, and finally gives the conclusions. Optical wireless communication has a lot of advantages compared with the radio frequency RF communication. For example, it has ultra-high bandwidth, no license fee, and it has inherent physical security. Therefore, it has been widely used in many applications, such as the urban free space optical communication, the UFSO system, and the underwater wireless optical communication, the UWRC system, as shown in Figure A and Figure B. In the OWC system, in order to achieve an energy-efficient and security optical link, people usually adopt the line of sight configuration, which requires very strict alignment between the transmitter and receiver. And the misalignment would cause the loss of optical signal and significantly degrade the communication performance. Therefore, alignment is very important. However, it also very challenging to accomplish because of the existence of the disturbance, such as vibrations, atmospheric turbulence, and etc. Moreover, maintaining a line of sight optical link is especially challenging for the mobile OWC system, because this kind of system are affected by both movements and disturbance. There have been several works to try to solve the alignment problem for the mobile system. For example, people propose to use multiple optical sources and multiple photodetectors, but this kind of configuration will render high costs and high complexity for the system. Some people propose to use a hybrid micro manipulator. However, it will be too complex to be applied in the real implementation and not robust to disturbance. Those two are the physical strategies. One of the control strategy proposed to use the extended common filter-based tracking control to solve this problem. However, this approach requires the nonlinear model of the system, which is computationally expensive. So in this work, we propose to use an extreme seeking control-based two-step control strategy to solve the alignment problem for the mobile OWC system. This is our experimental setup. As you can see in this figure, we use two smart robot cars as the mobile platforms, which are controlled by the Arduino microcomputers, and we use a laser and a photodiode, a PD, as the transmitter and the receiver. In the receiver side, the PD is directly mounted on the receiver car. And in the transmitter side, we use the vision sensor Pixel 2, which is a camera that has vision processing capabilities and is mounted on a pan-tilt mechanism. This mechanism has pan and tilt motors used to rotate the pixel's yaw and pitch angles, and also controlled by the Arduino microcomputer. Besides, we use 3D printing to print a case that can mount the laser on the top of the Pixel 2. This is the laser and this is the Pixel 2, so that the laser and Pixel 2 can move together wholly. This is our proposed two-step control strategy, which consists of coarse alignment and fine alignment. The input is the position coordinates of receiver in the image frame, X and Y. Once we get the position coordinates of receiver, it will check if there exists tracking error or falling error. If yes, we will use the feedback PD control to eliminate these two errors. And then for the fine alignment, we will use the perturbation-based extreme seeking control to resist the effects from disturbance. And finally, get the maximum received optical power, Pmax. Now let's go in deep to say how we realize the coarse alignment and fine alignment. Let's first talk about the tracking control. Tracking control is realized by the vision sensor Pixel 2. Pixel 2 will recognize the receiver by its specific color, and it will return back the information about the position coordinates, block size, and color code of the receiver. As you can see from the figure, here we have two errors, pan error and tilt error. And the objective here is to eliminate these two errors so that the receiver is kept at the center of the image frame, which means the transmitter keeps tracking the receiver. How to do that? Well, Once the Pixel 2 detects the receiver, the position coordinates x, y of receiver will be reported back to Arduino. And Arduino will use the feedback PD control to adjust the pan and tilt servos to make the receiver at the center of the image frame. And this is the control law. KP and KD here are the control gain. This is a very simple demo to show how Pixel 2 recognizes and tracks the receiver. As you can see, when the receiver moves, the Pixel 2 will rotate to track the receiver, as the black arrow shows here. Then, for the following control, it is realized by the smart cards. Same as before, we have two arrows here. One is the angle arrow, the other is the distance arrow. The objective here is to eliminate two arrows so that the transmitter card will directly face the receiver card at a certain distance, as shown in this figure. Once Pixel 2 recognizes the receiver, the position coordinates x, y, and block size of receiver will be reported back to Arduino. The position coordinates reflecting the angle arrow will be used to calculate the speed difference, and the block size reflecting the distance arrow will be used to calculate the forward speed. Arduino will use the P control to adjust the left and right drive motors so that we can eliminate the angle arrow and distance arrow. This is the control law. KP prime here is the control gain. After the coarse alignment, the transmitter card is capable of tracking and following the receiver card. However, because of the existence of the disturbance, the transmitter cannot be perfectly aligned with the receiver, although the error of the coarse alignment is 0. That's why we also need the extreme seeking control to do the fine alignment. The reason why we choose to use ESC control is because it is an optimal control strategy, which in our case aims at maximizing the received optical power. And it's a model-free control. We don't need to develop the complicated model of the system. And it can optimize the output only relies on the measurements. No need to know the cost function, and allows us to track an undetermined varying maximum of cost function. This is the structure of an ESC control system. You have the system showing here, y equals to hx is the output function. And for the ESC controller, you need to have a high pass filter, a low pass filter, and an integrator, and also need to introduce a sinusoidal perturbation. It works like this. For example, our cost function is a concave function. Now your input B is bigger than the optimum input B star. And when we introduce a sinusoidal perturbation, the output function will be like this. So the output and B are out of phase. So after integration, we will get a negative number, which will push our input back to the left side. On the contrary, if our control input B is smaller than the optimum input B star, then the output will be like this. So the output and input are in the phase. So after the integration, we will get a positive number, which will push our input back to the right side. Therefore, we can see this kind of scheme will make our input reach to the optimal input. And at the optimal input, we will get the maximum output. Now let's introduce the ESC controller into our system to realize the fine alignment. And we start with the model design of our system. Considering our receiver is a 3D point with coordinates capital X, Y, Z, it will project to the camera frame of Pixel 2 with the 2D point, whose coordinates is X and Y. We can relate the 3D point to the 2D points by the parameters of the camera, as shown in this equation. After the derivative, we will get this new equation. Now, relate the velocity of 3D point to the camera's spatial velocity using the Fermat's equation in reference 1, we will get the new equation shown here. Assuming capital Z is fixed and known, Z is the distance between the receiver relative to the pixel camera frame. We would get the reduced system showing here, which is a nonlinear model, I dot equals to A times control UC. After deriving the model, let's now design our ESC controller. Let's I tilde equals to Let I tilde equals to I minus I0. I is the position coordinates of receiver. I0 is an unknown constant vector. We call it a reference position. After derivative, we get I tilde equals to A times control input UC. If we're using the feedback linearizing control, UC equals to minus C A transpose I tilde. C is a constant here. But we have I tilde dot equals to minus C A transpose I tilde equals to minus C I tilde, which means I tilde will go to 0, which means I will reach to I0. For the power mapping function or set cost function, we choose this Gaussian-like distribution for both x and y axes. So as you can see, if we choose x to be x star, then px will be equal to px max. The same for the y direction. Now we have our system model. We have the control UC, and we have our mapping function for x and y. And we also have two ESC structures. The system works like this. If we let the reference position x0, y0 to be the optimal position x star, y star, by using the control UC, we will ensure that xy will reach to x0, y0, and so reach to x star, y star. And to realize that, we use the perturbation-based ESC scheme to adjust x0, y0 to x star and y star according to the power mapping functions. Therefore, we can see that the optimal position for the fine element here is where received power is maximum, rather than the central position in the cross alignment. Now let's see our simulation results. The table showing here are the values of the parameters for the two ESC structures. First, we consider about the static disturbance. Static disturbance means the static error. For example, after the cross alignment, the current position xy is at the center of the image frame, phi phi. However, due to some disturbance, for example, the car bumps into the wall, so the optimal position is not the center position anymore, but let's say 2 and 3. We give an initial guess of the reference position x0, y0, and assume the maximum power is 5 milliwatt. So as you can see from the figure, the reference position will go to 2 and 3 respectively, and the position of our receiver xy will decrease from 5, 5 to 2 and 3 gradually, and this is the variation of control input UC. Besides, as you can see, the received optical power will finally reach to the maximum power, 5 milliwatt for both axes. Now let's consider the dynamic disturbance. Dynamic disturbance means that the disturbance is not static. It will vary with time. To simulate the dynamic disturbance, we introduce two random noise for x and y axis. The current position is 5 phi as before, but the optimal position will not be the static value, but in the vicinity of 2 and 3. From this figure, we can see that the reference position will finally reach to the vicinity of 2 and 3 with very small variations. And for x and y, it will also decrease to the vicinity of 2 and 3. From the received optical power, we can see that if without adopting the ESC control, the received power will not be the maximum 5, and their variation according to disturbance are very big. However, after adopting the ESC scheme, the optical power for both axes are near 5 milliwatt, and the variation according to the disturbance is decreased a lot. So we can see that the ESC control is able to track the unknown varying optimum position. So in this work, we propose an ESC-based two-step control strategy to solve the alignment problem for the mobile OWC system. We adopt the simple feedback PD control for the cross alignment to realize the tracking and following. And for the fine alignment, we use the perturbation-based ESC control. We introduce about the model design, the controller design, and the ESC control scheme. The good simulation results demonstrate the capability of our proposed strategy. From a practical point of view, the proposed method is simple, effective, and easy to implement, and can achieve the optimum of communication quality even in the presence of varying disturbance. For the future work, we will try to do the real implementation according to our simulation results. That's all. Thank you for your listening.